right, so here's the new and improved um, webinar. For those of you who like a small picture in the corner, that is me in my kitchen wearing my headset, the Cleveland Browns sweatshirt my wife got me so that when I walk at night I won't get hit by a car. I like to call the thing in the back the duck blind. Tease my wife all the time that it looks like we're in the Russian roulette scene of the deer hunter when we eat dinner. That is not smiled upon. But she did get me a sweatshirt, so she loves me. All right, so this is periodic trends. We're just going to do a little bit of it. What we know so far. So valence electrons determine reactivity. When atoms encounter one another, it's these outer electrons that will be the first things that encounter another atom, and so therefore it's those valence electrons that determine reactivity. Noble gases are the most stable with 8 valence electrons, and stability is the goal of atoms. Things in the universe like to go to the most stable place. That's why rocks roll down hills, and that's why uh, we prefer napping. um, but stability is the goal of atoms, so they're trying to reach this stable 8 valence electron situation that noble gases have. So we could say they want to be like noble gases. They want to have part of that stability. So periodic trends is all about attraction, and I've used this picture to show this idea of a group of like-minded individuals. Here it's a group of women. We assume in this situation that they are attracted to these men who are surrounding them, and these men are attracted to these women who are in the center. So if this is your nucleus here, and these are our protons, they are trying to actively attract these electrons to the atom. They do so with a magnetic like attraction of atoms. And as a result, let's get actually to the next slide. So here's the situation of lithium. So you have 3 protons here, and it's trying to attract the 3 electrons. So it's a 1-to-1 situation. It's good, but there's a shielding effect. These 2 electrons here are sort of blocking this nucleus from really getting a full pull on this 3rd electron. It's not a lot. There's only 2 there, but that still exists. As we go down a group, sodium, here's 11 protons. The shielding is increasing because now there are 2 electrons in the first shell. There are 8 electrons in the second shell, and the third shell has this 1 lone electron. So for these protons to attract this 1 lone electron, they have to get through all this electron shielding. Going back to our picture, it's sort of like if this woman wants to make eye contact or get attraction going with somebody over here. Look at all the shielding, all these guys she has to sort of see through to get eye contact here. The shielding is what causes electrons to not be as drawn into a nucleus. So as we look on the periodic table, we know that each row, each period shows the number of shells, energy levels. And so this has 1 energy level filled. This second period has 2 energy levels filled. This is 3 energy levels. Then this is 4 energy levels here. And as a result, as you go down, there is less attraction to the outermost electrons, or increased shielding. And up here with helium, there are 2 protons in the center, 2 electrons in that first shell. So there's decreased little shielding here. Neon has a little more, argon has a little more. So the desire to keep your existing electrons increases in this fashion up toward helium, where francium has the least attraction to its outermost electron, and helium has the most attraction to its 2 electrons. All right, going down here. So size, you can see as the size down a group, lithium, sodium. So we're going down a group, down this group here. So lithium, sodium, we're increasing the number of shells, therefore we're increasing the size. Potassium has 1 more shell, so that's 1, 2, 3, 4 shells, 1 electron in that outermost shell. Sodium has 3, lithium has 2. They all have the 1 lone electron in that outermost shell. So in this case, that electron can determine the size of this atom by sort of floating a little bit away from the nucleus, and then the nucleus every now and again will draw it back in. So let's talk about size. Size has to do with the atomic radius. The atomic radius is sort of the distance from the nucleus to the outermost electrons. So that would be the atomic radius for lithium. For sodium, nucleus to the outermost electron. So it would be that big for sodium. And for potassium, the atomic radius would be from the center to the outside, like a radius of a circle, to the outermost electron. So you can see that this is increasing in size as we go to potassium. Likewise, going across a period, now we stay at the 3 energy levels going across a period. That's all the third period in this case. Sodium has 11 protons. The shielding of these 10 electrons is keeping it from drawing in this 11th electron. There's only 1 electron out there. It can kind of wander and make a bigger atom. When we have aluminum, now there's 3 electrons in that third shell, 13 protons trying to draw in 13 electrons, but now there's 10 as here, 10 doing the shielding, but there are 3 electrons out there. That's a little more, that makes that outer shell a little more important. There's more attraction in toward the nucleus. If you think of it back to the dance scene, so there's 13 women here, there's 10, in that case, men trying to divert the attention of those women, but now there are 3 men out here on the outermost shell, the furthest away. So there's 3 new protons in here trying to draw the attention of these 3 electrons. That is a situation that would make this become a little more compact than sodium with just 1 out there. And now argon has 8 in that outer shell. There's still 10 electrons doing the shielding, but there are 8 additional protons, 18 total, 10 to be occupied by these 10 electrons and 8 protons trying to draw in these 8 electrons. So there's much more drawing in. It brings the atom a little closer together. So the radius is going to be less for argon than for aluminum, and aluminum is going to be less than sodium. So the trend we see is right here, atomic radius. As you go down a group, you're adding shells, so things get bigger. And as you go across a period, the number of electrons in the atom are becoming greater, but the number of shells is not. So there's greater attractive forces to bring them closer to the nucleus. So that means you decrease in size. Helium would be the smallest, as you can see, and cesium would be the biggest in this case. Francium is below it, but this picture, which I like, only went to cesium. So you can see that trend continues for everything. The noble gases get bigger as you go down. The halogens get bigger as you go down. Size is increasing as you go down a group, and size decreases as you go across a period. All right, so here is the first ionization energy, which is, I believe, covered in the next one. So